All right, well, I'm going to talk about guided problem 2.6, which I promised that I would do the other day. I'm also going to do a somewhat thorough problem-solving process through this. Since this is a guided problem, it's got suggestions of the kinds of things that you should think about while you're working through it. And I'm going to talk about each of the things that it suggests. And I'll do most of them, and then in some of the cases, I'll say that I don't think it matters as much for this particular question. Okay, so the scenario is you've got a helicopter pilot who is trying to pick up somebody who's been stranded, a hiker. They're supposed to fly a distance d. Let me underline some important things. They're flying a distance d at speed v directly east to pick up the stranded hiker. They don't see the hiker there when they arrive. They radio the control tower and learn they actually went the wrong direction. It was supposed to be west, which means they went some distance the wrong way, and then they have to go back the other way, even farther to get to where the person actually is. So they're actually distance d west of the airport. They turn around and head straight for the hiker at a speed that's 50% faster than before. Okay. Then we got the questions we have to answer are about the x component of the helicopter's average velocity for the whole trip. And then given that the x-axis points east, and then what's the helicopter's average velocity for the whole trip? So those are the things that we need to figure out. Okay, so the problem statement, the guided part of it suggests, okay, well, why don't you draw a diagram representing the motion during the trip, indicating the position of the airport, the turning point, and the rendezvous location. Okay, so let's do that. I'm going to draw a diagram representing the motion during the trip. So we've got, let's see, we have the airport right here. We've got the location where the helicopter turns around after realizing they tragically went the wrong direction. So that's over here to the east. Let me draw sort of like a dotted line showing the trip. That's the location where they realize they went the wrong way after they call in, then they go back the other direction. Way over there. The same distance again on the other side. This is where the hiker actually is, over here. So that's the whole distance that they have to cover. Okay. So that tells the story, indicating the position of the airport, the turning point, and the rendezvous location. Okay. Label the eastward and westward segments with symbols. Okay. Well, first, let's draw like a little compass rose over here, showing that up is north, to the right is east, and to the left is west. They're only actually going to be traveling east and west in this trip, but I mean, it's useful to put in the north there. So then the eastward direction, since that's our positive x-axis, that's the I-hat direction. That's the x-axis, also I-hat. So that means when they're going to the east, they're going positive I-hat. When they're going to the west, they're going negative I-hat. Okay. Then indicate how your chosen symbols relate to the given information D and V. Okay. I'm not totally sure exactly what they mean by that, but let's say I say that this direction right here is D, and it's this location right here is D I-hat to the right of where the airport is. This location where the hiker actually is negative D I-hat because it's to the left, to the west. And then, I probably want to show something about what speed they're going, the velocity of each part. So in this leg, the velocity is plus V I-hat. So the V is standing for the magnitude of the velocity, and the I-hat is telling me the direction. And then in the return leg, as they're going all the way back from D I-hat all the way back, they're going, the velocity is negative 1.5 V I-hat. So the I-hat tells me the direction, the V tells me the size, the negative tells me it's to the west. I had labeled vector arrows to your segment to indicate the velocity in each segment, so that's what I've just done right there with the plus V I-hat, the negative V, 1/2 V I-hat. Would a graph of x of t be useful? Well, yeah, of course it would. Graphing things is always a useful thing to do. In fact, I would strongly suggest that almost always making a position versus time graph is a good idea. So let's try and do that. So position versus time. Time is only going to go forward. Position, let's say up is, that's the x-axis, that's in the positive direction or to the east. And anything downward on this graph, that's in the westward direction. So they start at the airport, which we'll call the origin, and then they, at some point, get to location plus d I hat. I'll label that in red, plus d I hat. And they're going at speed v to get there at a constant speed. And then they turn around and go back, and they're going faster on the way back. They're going 1.5 times more, 50% faster. So that means that on the way back, it's going to be steeper. And I'm not going to figure out exactly how much steeper it should be right here. I'll just draw it clearly steeper. And then they need to get to location minus d I hat at some point. Minus d I hat is the location. And I don't know what the times are. So really, for those two locations, I'm going to need to know what time is it? How much time has it taken to get to that point? So let me go back to the problem statements. All right, how does this problem differ from work problem 2.5? I don't know. I'm not going to look back at that one right now. It's a good idea in general to look at other problems and think about how they relate to this question, but not necessarily in all cases, and sometimes there isn't one that you can relate to. All right, because no numerical values are given, what physical quantities do you expect to be represented by algebraic symbols in your answer? Okay, so I expect to see D and V show up in my answer because those are unknowns that I'm given. So I expect D and V to show up in there. If they're not there, then they must not have mattered for some reason. And I really expect that the distance that you travel and the velocity that you're traveling at is going to matter for figuring out what your average velocity was. All right, part 7. Be careful about the signs of the x component of the displacement and the x component of the velocity in each segment of the trip. All right, it's always a good idea to be careful about the signs. Is delta x in the eastward segment positive or negative? Well, in the eastward segment, delta x vector is positive because that's when you're going in the plus I hat direction. Is v sub x in this segment positive or negative? That means the x component of the velocity. It's also positive because if you're going in the positive direction, your velocity is positive. What about delta x and v sub x in the westward segment? Okay, both of those are going to be negative when you're going on the way back because you're going westward, which is the negative I hat direction. How can those quantities be expressed in terms of v and d? Okay, we'll figure that out. But there's going to be some relationship between the displacements and the x component of the velocity and the given speed v and the given distance d. Okay. What time interval is needed to fly the eastward segment? Okay, here they're giving us a hint of like a sub-step that we need to figure out. So there's a time interval needed to fly the eastward segment. That's how much time it takes to get to the point where they realize they went the wrong direction. Let's call that T1. And I'm going to go down here and label that on this graph. That is time T1, the moment at which they realize they need to turn around. And actually this point right here, where they're at the location plus di hat, the coordinates of that point on this graph are T1 and plus di hat. Okay. And then what time interval is needed for the westward segment? Okay, how much time does it take to get all the way back to where they were supposed to be? So I'm going to label that one T2, the moment where they get where they're supposed to be, that means that this location is coordinates T2 minus d I hat. And we're going to figure out how much time it takes to do that. Okay, and then they give us another hint here. If you don't get positive values for both intervals, check your signs for delta x and v sub x. Okay, positive values for both intervals is talking about the time. The time has to be positive. Time intervals are always positive. So if somehow in our rearranging of algebra we get a negative sign, that means we did something wrong with the signs of the displacements or the velocities. All right, number 9, how can you combine this information to determine the x component of the average velocity and then the average velocity in vector form? There's a sort of guiding us toward how are we going to combine all the information that we've got already to figure out the things that we're looking for, those velocities. Okay, so that was all supposed to be about devising a plan, but I don't entirely feel like I have a plan yet. What I have is a diagram showing what happens. Airport, turnaround point, getting to the place where they're supposed to be. I have my axes labeled, northwest and east. I didn't draw south because nobody's going south. I've got east and west on this position and time graph. I've got the time when they turn around, the time when they get where they're supposed to be, and the two distances. Okay. So I think what I want is I want to figure out something about how much time it takes to get the whole trip. If I'm thinking about the ultimate question, which is what is the x component of the helicopter's average velocity, and what's the helicopter's average velocity? So average velocity. Okay, let's go to a definition for a moment. Average velocity is what? V average over some time frame is the displacement during that same time frame divided by the duration of that time frame. Okay, so to find an average velocity, I need to know what was the change in position, and I need to know how much time did it take. And then there's the complementary version of that for the x component of the average velocity, the average, actually I think they put it the other way around. The x component of the average velocity, like that, is the final position minus the initial position, the x coordinate divided by how much time it takes to do it. So both of those are basically telling me I need to know where it started, I need to know where it ended, and then I will figure out what the velocity is. Okay. So let me put in a little bit of information and see if I can use that to figure out what I need to do next. Let's say from beginning to end, what was the displacement? Okay. Well, the initial position, x initial, is 0. We're saying the airport is the origin. What's the final position? The final position is negative d I hat. That's when you get back to where the hiker is. Okay, so that means delta x vector is negative d I hat minus 0. So the displacement is negative d I hat for the whole round trip. And remember, the displacement doesn't care how you got there. Figuring out the displacement, it doesn't matter that they went the wrong way first. You just need to know that the starting location was 0 and the ending location was negative d I hat. Okay, so if I want to figure out the average velocity or the x component of the average velocity, I need to know the displacement, which I now know. So I need to know the displacement, which I now know. I'm trying to find the average velocity. I then need to know what the total time is that it took to do that. That's something I don't know. Okay, so let me fill this in a little bit more. V average velocity is delta x, which I now know, negative d I hat, divided by the amount of time that it takes. So that is my next step. So I'm beginning to formulate a plan here. And I'm basically working backwards. This is the thing I want. I know one piece of it. I don't know how much time it takes. Okay, let me go back to my drawing here. I represented that time. The total time it takes to get back is T2. Okay, so let's simplify this. Negative di hat over T2. So I've put that in terms of what's in my drawing. I don't know what T2 is. So T2 is now a thing that I need to figure out. So T2 equals, I don't know. Now I'm going to need to figure out what that is in terms of the other things that I do know. So in order to figure that out, I've got two legs of the trip. I've got T1, where I know what the speed is, and I've got T2, where I know what the speed is. Okay. So for this forward leg, I know that the velocity is v. I know that the distance is d, and I know that the time is t1. What I'm using there is that velocity is distance over time, and I know the velocity isn't changing. The speed isn't changing. So I'm going to solve for t1. That tells me that t1 equals d over v. Okay. Cool. I now know what t1 is. What about this time frame from t1 to t2 when they're traveling 1.5 v? So during that time frame, I have 1.5 v equals 2d, because they had to go all the way back to where they started from and then that same distance d again, divided by the difference between the two times, t2 minus t1. t2 minus t1. So that means that t2 minus t1 is 2d over 1.5v. Okay, I've learned some more things. I now know the duration of time it took to get to the wrong place and the duration of time it took to get back to where they were supposed to be. So the total time, which is t2, has got to be the sum of those other two. So t2 is equal to t1 plus t2 minus t1, which maybe that looks a little bit silly to write it like that. That's obviously the same thing as t2, because if you subtract the t1, you get just t2 left. But t2 is the thing I actually wanted to find, and I've got expressions involving those durations of time. So let me take those and put them in. I'm going to take this one and put it in for t1, and I'm going to take that one and put it in for t2 minus t1. So that gives me t2 equals d over v plus 2d over 1.5v. Let me put a new page here to work with. Okay, let me simplify this expression so that it looks a little bit more readable. So the total time that I want is d over v plus 2d over 1.5v. I like to do things in improper fractions. It's a little bit easier to deal with. t2 equals d over v plus 2d over 3 halves v. 1.5 is the same as 3 halves. And then I can flip that over to get d over v plus 4d over 3v. And then I can get a common denominator by multiplying the left one by 3, and you get 3d over 3v plus 4d over 3v. And that becomes 7/3 d over v. So that is the total amount of time that it takes. Okay, so what do I need to do next? I've got the total time it takes for the entire round trip. That was a thing I definitely need for both of these questions, for the x component of the average velocity and for the whole vector average velocity. I need the amount of time, and it's the same time for both of those. And then to find the actual average velocity, I need the displacement during the entire time, or the change in the x position, which in both cases is negative d I hat. It's negative d I hat for the vector change in position, and it's negative d for the x component of the change. So I'm going to take that v, that delta t. So v vector average is delta x over delta t. Delta x is negative d I hat. The change in time, the duration of the time is 7/3 d over v. And then that is going to give me an average velocity of negative 3/7 v I hat. That is actually the answer to part B, the vector average velocity. Does it make sense that it's negative? Yes. At this point, I'm doing the evaluate part. Does it make sense that velocity is negative? Yes, because the net displacement was to the left, was to the west. Therefore, the resulting velocity should be to the left, negative. Does it make sense that it's a fraction of v? Well, yeah, it makes sense that v should be in there somewhere, so it should be a function that has v in it, because v was the speed they were going at for part of it, and 1.5 v was the speed they were going at for another part of it, so v should be in there somewhere. Does it make sense that it's 3/7, that it's smaller than v? Yes, because they spent a big chunk of the time going the wrong direction. And since the displacement doesn't take into account the fact they went the wrong direction, this average velocity is going to end up being lower than the average speed was. Okay, so then part A asks, what is the x component of the average velocity? Well, the x component is negative 3/7 v. This is the x component without the I hat on it. In this case, this is one of those ones where the distinction between the vector average velocity and the x component of the average velocity seems a little bit moot because there aren't any other components, because the helicopter doesn't go north and south at all. And apparently doesn't change its altitude at all either. All right, so those are the answers to the two questions that were asked. I'm going to extend it a little bit and ask, what's the average speed for the whole trip? Okay, well, the average speed for the whole trip depends on how much distance was actually covered and how much time it takes. So average speed, which would be v av without the x component part and without the vector sign. So like I've said in class, this is a little bit of unfortunate notation. We don't have a separate one for speed, so we use v, even though that means velocity. And the way you calculate that is you ask, what was the distance traveled and how much time did it take? Well, I already know how much time it took. It was 7/3 d over v, which is hidden by my face in this picture right now. Right there. 7/3 d over v is how much time it took. And then the distance, let's see, let's put 7/3 d over v right there for the time. And the distance is 3 times d, because they went the wrong direction by a distance d. Then they went back a distance d, back to where they started from, and then a distance d again to get to where they were supposed to be. So that's a total of 3 d's that they traveled. So 3d. And then we simplify that fraction, and you get 9/7 v is the average speed. Okay, let me ask again. Does that make sense for an average speed? Does it make sense that it should be proportional to v? Yes, it should be something related to v. It should be a function of that, because that was how we figured out what the speed was. Does it make sense that it's more than 1v? That's faster than v? Yes, because for some of the trip they were traveling faster than v. Does it make sense that it is more than 1v and less than 1.5 v? Again, yes, because The speed was never higher than 1.5 v. It was never lower than v, so the average should be somewhere in between. Okay, one more subtle point. Why is it that it's not halfway in between 1 and 1.5 v? If you work this out, it's not halfway in between. It's actually a little bit closer to the 1.5 v. You should think about that. Why is it where it is in the line between 1 and 1.5? All right, that is it. Let me quickly go through what we did. We drew a drawing. We made an axis showing what our I hat and east and west mean and how they correspond to this drawing. We made a position versus time graph. We, in order to figure out where to start, we wrote down some equations about the vector average velocity and the x component of the average velocity, and said, okay, well, we must need to know, since really we know what the delta x is. We know the displacement is negative d a hat. The thing that we really need to figure out, the hard part, is going to be finding out how much time it takes. So then we wrote down some things about the velocity on the eastward trip and the velocity on the westward trip, and used that to figure out how much time it took to do the whole thing. We simplified that, and we got negative 3/7 v for the average velocity. And then we also figured out the average speed by taking the distance divided by the amount of time, and found out that that was between 1 and 1.5 v. All right, thank you.